Good afternoon. So, we come to the end of this week 6 and today we will take up some tutorial problems and we will do it step by step, so that we have the familiarity with the concepts that are discussed and which will also help you in doing the tutorials in this week. So, let us look at the first problem. The first problem says that an absolute velocity of water at the impeller exit is 14 meters per second at an angle of 18 degrees. So, when we talk about absolute velocities, the angle corresponding angle is alpha 2. In the problems that we will be giving you in the tutorial set, we will not mention it as alpha 2. In the worked out example today, I am talking about alpha 2, so that you can connect and remember that alpha is the angle which the absolute velocity makes. The blade peripheral speed or u at the exit is 25 meters per second, shaft speed is 1450 rpm. Whirl component of the absolute velocity at inlet is 0, the flow rate is 18 liters per second. Please take care of the units, you have to be consistent. So, convert this into meter cube per second and find the magnitude of the relative velocity and its flow angle beta 2. Also find out the power required, assuming that the pump efficiency is 100%. We will solve this problem for pump efficiency of 100%. If the pump efficiency is different from 100%, you should be able to take it into consideration by the suitable factor called the efficiency. So, in these sort of problems, my suggestion is always draw the velocity triangle and write down what all are given. So, this is the exit velocity triangle, which C2 is the absolute velocity, W2 is the relative velocity and U2 is the blade peripheral velocity, all at the pressure side or the exit. Alpha 2 and beta 2 are the corresponding angles, Cu2 is the whirl component and Cm2 is the meridional component. And at the inlet, since it is given that the whirl component of the absolute velocity is 0. So, we can write C1 equal to Cm1 and the corresponding other velocities are U1 and W1. What is given is C2 equal to 14 meters per second and alpha 2 equal to 18 degrees. We also know that the RPM is given 1450 as n we have written and U2 as 25 meters per second. Cu1 is 0. Volume flow rate is 18 liters per second, as I said, convert it into meter cube per second. We need to find out the relative velocity, means we need to look at the triangle at the pressure side. So, let us look at the triangles again. Okay. So, we are talking about C2u or Cu2, the notations can be used in different ways, but both are consistent. So, Cu2 or C2u are the same quantity is C2 cos alpha 2, which is 13.3 meters per second. You can work it out, the values you can get from the relationships, and C2m is related with the sin alpha. So, C2 multiplied by sin alpha 2 is 4.33 meters per second. Thus, we know this is 4.33 meters per second and Cu2 is 13.3 meters per second. So, what is WU2? WU2 is the corresponding projection of W2 along U2. So, this distance is what we are talking about. This distance is WU2. And here when we are talking about it, we can find out the WU2 or W2u is U2 minus C2u is 11.69 meters per second. And we know that C2m or Cm2 is equal to W2m and it is equal to 4.33 meters per second. So, now to get W2 is nothing, we know W2m and W2u. So, we can find out W2 to be 12.46 meters per second and beta 2 can be found out by the tan of beta 2 we know is W2m by W2u and hence beta 2 is tan inverse of W2m by W2, which is 20.3 degrees. And coupling power in this case is the blade specific power, because there is no losses. We have talked about 100% efficiency. So, we can see coupling power equal to PBL is equal to rho V dot U2 Cu2 minus U1 C1, but Cu1 is 0 and hence we get that coupling power is 5.99 kilowatt. We can continue with this problem and add some more complexities. We can say that the outer diameter of the same pump which we have talked about, we need to find out, and if the inner diameter is 60% of the outer diameter, can we find out the inlet blade angle beta 1. It is given that the meridional velocity is constant, which means C 1 m equal to C 2 m. So, as before, we will draw the velocity triangles, and taking the data which we have already obtained in the first problem and along with what is given, let us write down. It is already given that C 2 is 14 meters per second and alpha 2 is 18 degrees. The blade rotational speed was also given along with the blade peripheral speed. Volume flow rate was also given. We know the relationship that U 2 is equal to pi n d 2 by 60, and hence d 2 can be obtained as 0.329 meters. We know that U 1 by U 2 is equal to d 1 by d 2. Basically, U 2 is pi n d 2 by 60 and U 1 is pi n d 1 by 60. Hence, U 1 by U 2 will be d 1 by d 2, and we can get U 1 as 15 meters per second. Now, look at the velocity triangle at the inlet or the suction side. We know U 1, and since it is given that C m 1 equal to C m 2, we can say that both are 4.33 meters per second, and hence we can find out beta 1. Beta 1 is tan inverse C 1 m by U 1, which is 16.1 degree. Okay. So, what did we do? We have found out the velocity triangle information given in the outlet or the pressure surface, and then obtained the corresponding relationships which we require for the inlet or the suction surface, suction side. And we can continue with the same problem. We want to find out the blade height at the impeller exit, which is B 2, neglecting the vane thickness. That is, we know the volume flow rate, and you know from the classes that we have done in the last class, we talked about the volume flow rate in case of a radial flow machine is nothing but pi times d times b times the corresponding meridional velocity. So, we will use that relationship here. As before, we are talking about the velocity triangles. We write down what all are given, the C 2, alpha 2, U 2, volume flow rate and diameter. We have also obtained diameter d 2. So, we can write, and we know the C 2 m we have calculated and obtained it in the first problem. Assuming the 0 thickness of the vanes, we can write that V dot is nothing but pi d 2 b 2 C 2 m, which will give me b 2 to be 4 millimeters. Now, you can do this problem yourself by assuming that the blades occupy, let us say 5% of the vane passage, or blade thickness is accounting for 5%. So, then you can write a factor with a phi here, which is equal to 0.95, and you can find out B 2. I leave that as an exercise for you, and a similar problem where the blade height has to be obtained in case of a finite vane thickness is given for your practice. Finally, I come to the last problem where we want to find out the degree of reaction. We know from the previous 3 problems that C 2 is equal to 14 meters per second. We know U 2 is 25 meters per second. We know W 2 is equal to 12.46 meters per second. All these were either given or obtained in problem 1. Now, we also know from the second problem that U 1 is 15 meters per second, and C 1 is nothing but C m 1 as I have written here, and C m 1 equal to C m 2, it was also given. So, we can say it is 4.33 meters per second, and we can find out now W 1 here in this velocity triangle is right angle velocity triangle, and hence W 1 is nothing but square root of C 1 square plus U 1 square, and we get 15.61 meters per second. So, now we have obtained, or it was given to us, C 2 U 2 W 2 and U 1 C 1 W 1. So, we can find out the degree of reaction as U 2 square minus U 1 square plus W 1 square minus W 2 square divided by C 2 square minus C 1 square plus U 2 square minus U 1 square plus W 1 square minus W 2 square, and that will give me R, or the degree of reaction, as 0.73. So, these are the some of the problems. While solving these problems on pumps, turbines, or any turbo machine, please keep in mind that you should draw a neat picture of the velocity triangles and try to draw the angles, not you do not have to make it exact, but try to make it looking close. For example, if beta 2 is given as some value which is acute, try to draw it acute, because then you will have a proper idea of how Cu2 is working, is it more or less, and then try to work out the triangles properly and get what are the informations which are missing. And rest of the problem is actually application of suitable formulae. The crux or the most important part of turbo machine that we will be covering here, we have covered so far and we will be covering in the coming lectures, is understanding a problem, translating that problem into suitable velocity triangles and determining different components, and then plugging these components into the relationships as we have done here. I hope that if you do the tutorials, these portions will become clearer. In the next week, we will start the pumps and we will revisit some of the problems that we did today in more details. We will talk about the pump performance and the related problems, and some of the concepts that we did here will also become more relevant and more meaningful with the practical example of pump. Thank you.